Welcome to the second narrated PowerPoint for Lecture 2 of BBE 4023. This narrated PowerPoint will cover sensor and transducer sensitivity and the difference between precision and accuracy. Let's begin this section with a question. Would you believe a colleague that told you that they had just measured the temperature in the room to be 61.435 degrees Fahrenheit or 16.353 degrees Celsius? Yes or no? Would you believe your colleague? Well, I would probably have some questions about the reading. And that's an important point about instrumentation. You want to be skeptical and questioning when working with instruments. Most people assume that if a machine or device says that it is 61.435 degrees Fahrenheit, well, it must be. But that's not always the case. There are many reasons that a reading might be incorrect. The first question is, what do I think the room temperature is? Some people call this a sanity check or reality check. 61 degrees Fahrenheit is fairly cool. Do I feel cool? If not, maybe the sensor used isn't reading correctly. Is the room heated? Air conditioned? If the windows are open, what was the predicted ambient temperature? Is sunlight heating the room? The second question is, how did my colleague measure the temperature to within plus or minus a thousandth of a degree Fahrenheit or Celsius? That is not done with an ordinary temperature sensor or transducer. So my colleague must have used something special. It would be important for my colleague to report what device was used to measure temperature with such precision. It would also be important for my colleague to communicate how the temperature sensor was calibrated to such a precision and accuracy. Calibration is always important. Without proper documentation, I would question, be uncertain about what my colleague had told me. If my colleague provides the proper documentation, then I would trust the information. To answer the specific questions listed, the measurement is precise. We don't have enough information to know if the measurement is accurate. This slide lists common instrumentation characteristics that you need to consider when selecting or purchasing an instrument. Some of these terms have particular meaning in relation to instrumentation. Some of these terms we will define today, and some will be covered later. 2 points to remember when shopping for an instrument is that there are many factors and characteristics that you need to consider. This is only a partial list. So when you anticipate purchasing or selecting an instrument, it is important that you begin to determine what level of sensitivity, linearity, range, accuracy, precision or resolution, repeatability or reproducibility you need for your situation. The second point is that these are important terms that you will need to understand in this course. You will be introduced to many new terms in this course. Sensors interact with the world. They sense a change. An input change as the world changes, which produces an output change which we use to measure the input change. The ratio of the output change to the input change is defined as the sensor or transducer sensitivity. This ratio is shown as the slope of the lines drawn on the graph. The graph is a plot of the sensor output on the vertical axis versus the sensor input on the horizontal axis. Ideally, a sensor responds to only one changing input. Unfortunately, many sensors and transducers have a dual sensitivity to temperature. This means that the sensor output changes as temperature changes even if the input does not change. So dual sensitivity means that the output is a function of one or more changing inputs or environmental conditions. If the sensitivity of the second changing factor is small, it can be neglected. Temperature is a common factor that affects many sensors. If very accurate results are needed, check dual sensitivities and the temperature coefficient on the spec sheets. This slide shows the linear response of three sensors with different sensitivities. The solid black line has approximately a unit slope, 1 unit output change per unit input change. The red dotted line, the top line, produces a larger change in output per unit input change. The red dotted line has a high sensitivity. A small input change produces a relatively large output change response. The blue dashed line, the bottom line, has a low sensitivity. It takes a large input change to produce much of an output change. This graph can also tell us the input range that each transducer can be used over. Note that the transducer corresponding to the red dotted line has a small input range and a large output scale. The transducer corresponding to the blue dashed line has a much larger input range but a small output scale. When purchasing a sensor or transducer, it is important to know what input range you need or plan to use the transducer to measure over and what kind of sensitivity you need. It is usually difficult to have both a large input range and a large sensitivity. The three lines shown here show a linear response between input and output. Most sensors do not have linear responses. Many sensors have nonlinear responses. Thermocouples, for example, which are commonly used to measure temperatures, commonly use ninth-order polynomials to describe the relationship between the input temperature and the output electromotive force voltage. Sometimes linear equations are used to approximate the nonlinear response of a sensor. As shown here, a linear equation used to approximate a nonlinear sensitivity introduces some error into the output. If the error is small, it is okay. If the error is too large for your needs, it is not acceptable. We'll talk more about acceptable uncertainty and error later. And the next point in this presentation is the difference between precision and accuracy. In the instrumentation world, precision and accuracy have different meanings. They are not synonyms. Precision refers to number of significant digits. In the initial example at the beginning of this presentation, our colleague was reporting temperature with 5 significant digits. That is very precise. Precision is also related to measurement repeatability, the ability of a sensor to give the same or repeat the same output for the same constant input. Precision also depends upon the A to D conversion resolution. Analog to digital conversion was covered in the first lab, and will be mentioned again in future labs. Precision can be estimated by repeatedly measuring a constant input. Precision is indicated by significant digits, which were talked about earlier. Greater precision usually means more cost, so devices with greater precision generally cost more money. Don't use excessive significant digits. Giving excessive significant digits misleads the reader and gives the impression of greater precision than is real. Remember the opening example. Accuracy refers to the closeness of a measured value to the true value. How close is the measured value to the true or correct value? Spec sheets often report accuracy of a device as a percent of full scale, FS. For example, if a spec sheet says that your device has an accuracy of plus or minus 2% of full scale, and the full scale of the device is 10 millivolts, then the accuracy of the output is 0.02 times 10, which equals 0.2 or plus or minus 0.2 millivolts. Accuracy is confirmed by calibration. You'll want to calibrate a device against something that has 10 times or an order of magnitude better accuracy than the device being calibrated. For very important measurements, it may be necessary to trace or confirm the calibration back to the National Institute of Standards and Technology. They keep very accurate standards and can calibrate devices. Use standard operating procedures for quality assurance and quality control to achieve and maintain the stated accuracy of your measurements. Poorly maintained sensors and instrumentation systems will over time lead to inaccurate readings. This brings us to the end of the second section of the material for Lecture 2. In this section I introduced instrumentation characteristics, sensitivity, dual sensitivity, and explained the difference between precision and accuracy in the instrumentation world. The next narrated PowerPoint, Lecture 2, Section 3, will discuss measurement uncertainty and measurement error. This is the end of Lecture 2, Section 2.